tell me at first, but it's actually much easier than it looks. If we review what a UART signal looks like, you have this initial start bit. It starts off high, then you get the start bit, and then these are just arbitrary data bytes that could be any value. Then you have the stop bit, which is always 1. So let's just kind of walk through the process of what happens when a UART signal is received. So we send some byte through the computer, through plenty or something. It reaches this FPGA, it converts it to UART. So we get this waveform that's going to be generated onto here, going to this ADC. Starting with the clock div, I have clock divide 86, which basically just is a clock divider that outputs a slower clock signal than the 50 megahertz clock. And you can see the output of this clock divider feeds straight into the trigger. So that means this Mercury ADC is constantly triggering over and over and over again. So what's happening is that it's constantly reading this input right here. You can see I'm hooked up to channel 4 here, which is the channel that I plugged in. Actually, channel 4 is wrong. This should be 5. I'm hooked up to channel 5. So I'm constantly reading channel 5, which the FPGA is plugged into, and I'm getting a single-ended input. So that's all that I did with this Mercury ADC. So it's constantly sampling over and over and over again, and it's constantly outputting a new value to this register. Now this register is hooked straight up to the data input into the optronics, but it also hooks up to this FSM logic analyzer. And all this thing does is it just looks at this value and waits for that drop. So when it sees that the ADC is at one value, but then it drops to the next value, then it just uses a simple go signal to say, okay, now we have a start bit, so let's start capturing. That's all that this thing does. So you could have some output coming from here, but then once it drops below a certain value, then it raises the go signal, which you can see connects to right enable, which makes sense because we want to start capturing. So if we raise right enable, then that means we're going to start capturing. But go also attaches to this count 800 device, which all it does, this is actually a bit misleading because it actually counts from 100 to 800, and 100 to 800 is outputted here. So what happens when we receive a start bit, it will raise go high, it'll see that go is high, so the address out counts from address 100 to address 800 and connects to here. Now all it does is, once it gets to 800, then it outputs stop, and then stop connects to here, and then the FFM sees that we reached 800, then it lowers go again. And that's when we stop. And you can also see the clock divider connects here. It drives kind of like the timing, so count 800 appropriately counts a defined rate that I want. I don't want it to capture the waveform too fast or too slow. I want it to capture a specific amount. So the clock div 86 module is a module that determines the rate at which I sample the Mercury ADC and record data points with the counter so that the 9600 UART waveform fits nicely on the screen. So how was the division of 86 chosen? Well, when the waveform is captured, I want it to be centered on the screen. So let's say this is my VGA monitor. When I capture the UART signal, I want it to be padded by 100 pixels on the left and 100 pixels on the right. So it fits nice and evenly. So start off high, and then there'll be the start bit, and then it'll just be whatever bits are just sent over UART. So I kind of want it to look like that, where start bit, data bit, and stop bit. So that's one reason why I start at address 100 on the counter module, and then I only want to sample this waveform fast enough where I approximately get the end of the stop bit at address 700. Because if I sample too slow, then the waveform is going to be really tight and condensed, because it's just going to appear as a short amount of time. And if I'm too fast, then the waveform is going to be stretched out, and then I might miss a component of the waveform. So it's important to figure out the correct sampling rate at which I want to grab this data, so that way it fits nicely on the VGA monitor. So 9600 baud means that it takes 1 divided by 96 equal to 0.104 milliseconds to transmit a single bit. Well, there are 8 bits plus the start and stop bit. So you multiply that value by 10, which is just going to be 1.04 milliseconds. So the entire waveform of the UART message will take exactly 1.04 milliseconds. Now, if I want the beginning of the start bit to start at address 100, and I want the end of the stop bit to end at 700, then I have 600 data points to sample the waveform. So 1.04 milliseconds divided by 600 is just equal to a rate of 1.736 microseconds per pixel per address across the screen. So every 1.736 microseconds, I want to record a data point, then I want to wait another 1.736 microseconds and record another point, and so on and so on. Now the FPGA clock is 50 megahertz, and the period of that is 20 nanoseconds. 1736 nanoseconds divided by 20 nanoseconds is 86.8 clock cycles. So it's going to take 86.8 clock cycles to reach 1736 nanoseconds. So I want to record a data point, count 86.8 clock cycles, record another data point, wait 86.8 clock cycles again, and record a data point all the way up to address 800. Now with the module, I just simply round this down to 86. and there's a reason why I rounded down instead of up, but I'm going to just cover that later. Down here is where I have the method where I read the UART waveform